Okay, guys. So as I was supposed to take supposed to take class on few topics, so I'm just going through those topics, and I'll start the class. Let everyone join. Only 4 people have joined class on few topics, so I'm just going through those topics, and I'll start the class. Let everyone join. Only 4 people have joined class on few topics, so I'm just going through those topics, and I'll start the So I request all of you to kindly sit with your physics book, because mostly I would be referring that book only. Um, because this class would be focused on your exam. Is anyone else joining? Okay, I'll start the class. No issues. People are not joining, then I cannot help it out. So the first concept that I'll be taking up today is moving coil galvanometer. So what is a moving coil galvanometer? Why it is used? What is the usage of it? So moving coil galvanometer is a kind of ammeter. What is the use of ammeter? To find the magnitude of current in any current carrying conductor. Now, now then, why do we need moving coil galvanometer? So moving coil galvanometer will not only tell you, it will tell you also about the presence. I mean, if it tells the magnitude of the current, presence of the current is established, it will tell you two other things. So it will tell you two things. So it will talk about I, and it will talk about direction of the current. So first thing first, about moving coil galvanometer, it gives you two things. It gives you magnitude of the current. It gives you direction of the current. Now try to understand here. Let me download a moving coil galvanometer. Now look at this. This is moving coil galvanometer and how it is constructed. So I'll talk about construction of the moving coil galvanometer. So in construction of the moving coil galvanometer, you have two terminals. So here you see you have two terminals here. One is your positive terminal and second one is your negative terminal. And then you have these magnets. So this is your south pole of the magnet, and this is your this is your north pole of the magnet, and this is south pole of the magnet. Now this magnet is a kind of cylindrical magnet. So why do we need cylindrical magnets here? Though it looks bar magnet here, generally we use cylindrical magnet over here. We need cylindrical magnet in this particular construction because we need radial direction of the magnetic field to be radial. Why do we need direction of the magnetic field to be radial? Because suppose you understand that, suppose in between you can see here coils, conductor coils are kept over here. So these coils are copper coils which are insulated thinly, and in between you have a iron ore or soft iron cylinder which is placed inside it. So what happens over here is that when a external magnetic field, as I have already told you in the class, that whenever an external magnetic field would be there and a current would be applied to the conductor will feel a force which is I L cross B. Now what do I mean by radial magnetic field? So I'm removing this particular let me go to the. So look at here. What happens? Suppose I have a coil like this. So magnetic field is radial. It means that plane of the current carrying coil is in direction of the magnetic field. So this is the plane of the current carrying conductor and this is the direction of the magnetic field. Now what will happen if the plane of the current carrying conductor is in direction of magnetic field? Suppose this is B1. So on these two particular wires I will not feel any, or on these two particular wires there would be no current applied, sorry, no force applied, because F is equal to I L into B. If I and L are in same sorry, L and B are in same direction, so angle between them would be 0 degrees, so the force applied would be 0. While on other two conductors there would be force applied. So what will happen on this conductor? Suppose current is going in this direction and B is in this direction. So if I use right hand rule, so I'll put my fingers in this direction and I'll put palm in this direction. So a force upward would be applied. Here a force downward would be applied. So what will happen? Because one force is acting like this and one force is acting. If I take correct complete coil like one wire like this, from one side the force would be applied like this and from one side the force would be applied like this. So here if the force is in this direction or upward direction, here the force would be towards downward direction. So what will happen due to this force acting on two different coils, force acting in two different directions, the coil will start rotating. And as soon as the coil will start rotating, what will happen is that here is the elastic spring. So what happens as soon as this coil starts rotating, there would be some tension which will be developed in this elastic spring. So due to this development, I mean, as soon as the tension develops in this elastic spring and this coil starts moving in this particular direction, suppose it goes in this direction, so what happens, this will make certain angle with horizontal, this particular spring, and this angle can be measured out. As soon as I measure out this angle, so there is one formula. I'll just give you the formula. So in class 9th, you might have studied torque. So what happens when two forces are acting, something like this? So what happens? There would be torque developed on this body, and due to the torque developed, this will start rotating. The same will happen with the coil. That's what I was explaining on the other page, that whenever a radial magnetic field will cross this current carrying conductor, so on the parallel wires there would be no force, but on the vertical wires there would be opposite force from two sides. Due to this kind of opposite force, a torque would develop. Due to the torque, this spring would get elongated, or this spring will make certain angle with horizontal or vertical, whichever angle you take. So what is the torque developed would be n is the number of coils, I, because this is the total amount of current, into B and multiplied by A, and that this torque would be equal to whatever is angle, whatever angle this particular thing is making. This is not given in your book. I am explaining it from my side so that you can understand how do I measure current. I know number of coils in the conductor. I know what kind of magnetic field I am producing. I know the value of A. I just measure the value of theta here, And as soon as I measure the value of theta, so this torque would be equal to c theta, where c is torsional constant. So if it is a torsional constant, what will happen? So if it is a torsional constant, I know the value of constant also. So from here I can find that I is equal to c theta divided by NBA. So I know all these quantities. That's how I can measure I from here. So this is what moving coil galvanometer is. Is there any doubt in this? Any doubt? Tell me, guys. Okay, so one second, guys. Give me a moment. A is cross sectional area, and C is torsional constant. You don't need to know the value. This is a constant which is called constant of torque or torsional constant. So I'm not giving you values of this. You just understand that here, as soon as the torque will develop, this will start rotating. Due to rotating, this spring will lose its initial condition and it will make some angle theta. As soon as it makes some angle theta, this can be measured out. As soon as you measure it out, measure it out, you can find out the value of I. So that is the thing. So I'm moving to the another topic. Where leveling screws has been given, Ravi Kiran, let me go through your this thing. Time. See, I'm getting so many questions. Age, cross sectional area of the coil material, and C is torsional. C is torsional constant. I'm not finding Ravi Kiran. Where in the picture? What you are asking? Leveling screws. Where are leveling screws? See, it has been placed on this particular thing is placed on certain base. So leveling screws are not for this. Leveling screws are to put this base in proper manner so that the base doesn't start moving here and there. That's what this is for base. The construction is here. This is the construction of your moving coil galvanometer. You just know the construction that these are the magnetic fields which provide external. These are the poles, magnetic poles which provides external magnetic field. This is the moving coil galvanometer. Radial magnetic field is produced like this. Why we need radial magnetic field? I told cylindrical. I'm sorry, it is hemispherical. So hemispherical in nature. These poles are hemispherical in nature, which are able to produce um, radial magnetic field due. And when you pass a current through it, what will happen? Force would be applied on the coils of the conductor. So parallel coils will not have any force. Vertical coils will have, I mean, these wires will have force, these wires will not have force. And due to force acting on two ends of this complete coil arrangement, there would be torque developed into it. Due to the torque, this will start rotating. As soon as it will start rotating, so this particular spring will have certain angle with horizontal. So this is the formula NIBA, which has been given equal to C theta. So from here I know theta, I know C, so I can find out the value of I, that how much current is passing through it. So as simple as that. So any other particular concept that you want to know? Tell me. So I'm not getting any reply. So let me move ahead. What else do you want to? So now conversion, you can already see it has been given in the question. That, one second, I'm okay. What is the other topic? I'm just going through the list of topics. Just give me a moment. So now there is a concept of electromagnetic induction. So now I'll teach you electromagnetic induction and what happens in electromagnetic induction. So what is electromagnetic induction? A little bit of brief I have already given it to you. So what happens in electromagnetic induction? So I'll in this particular thing, I take moving coil galvanometer. I have already taken. So I will be taking your electromagnetism and generators and motors. All these things I'll cover up now. So let me go to electromagnetic induction now. So let me make the diagram for electromagnetic induction. So till now what we have studied is whenever a current carrying conductor is placed inside a magnetic field, a force is applied on the conductor. Now suppose I have kept a coil. This is my current carrying conductor in form of coil, and I have a magnet here. Suppose whatever you take, north pole and south pole like this. So suppose distance between it is d, and I don't touch this magnet, so certain magnetic field would be crossing this particular conductor. Now what I start doing for experimentation is that I keep on changing the distance between this coil and this magnetic material continuously. So this will never be d, it will always keep on changing. If I keep on changing distance between this magnetic material and this coil, what happens is the amount or magnitude of the magnetic field, or the magnetic field lines which would be crossing this particular coil, will keep on changing always. And as it will keep on changing always, what happens is, due to, remember always, due to change in magnetic flux crossing a conductor, a voltage difference, which is also called EMF, electromotive force, which I'll not use EMF, I'll use voltage. So a voltage difference would be induced in this coil. So what is happening? What I am doing? I am I am putting this particular current carrying conductor in varying magnetic flux, and due to this varying magnetic flux, a voltage difference is induced across its terminals. So what happens? This kind of electromagnetic flux, which is induced due to change in magnetic flux, is is known as electromagnetic induction. Why it is known as electromagnetic induction? So suppose there is no current in it. So let me draw it again. Suppose there is no current in it. I have just kept this I have just kept this coil like this. There is no current. I is equal to 0 initially. Now what happens when I place this particular coil in a magnetic field which is varying? Changing electromagnetic flux means either the distance between this and the magnetic pole or magnetic material is changing, or somehow I am changing the magnitude or the direction of the magnetic field passing through this particular current carrying coil. Due to change in this magnetic flux, what happens? A EMF is generated or a voltage difference is generated. If voltage difference is generated, what will happen? V is equal to IR. So this V is induced in this particular coil because of changing magnetic flux. As this V has developed, this particular coil will have certain amount of resistance in it, and due to it a current will start flowing through this conductor if the circuit is closed, and the value of current would be I is equal to V by R. So that is what electromagnetic induction is. Now the other rule of electromagnetic induction is that the whatever this voltage difference, so whatever V is induced, it is directly proportional to the rate of change of flux. So if I assume that, try to understand, if let's say that the flux is, Suppose I denote flux by phi. Suppose I denote flux by phi. So what happens? This phi keeps on changing. So V is proportional to rate of change of flux. Rate of change of flux would be d phi by dt. So V I can write down as n d phi by dt. Now try to understand, there are two, three things that I would like to clarify over here. The first thing that I would like to clarify is the EMF around this, or the voltage difference around this particular coil, is getting created only because varying magnetic field is crossing it. As soon as the magnetic field becomes constant, this voltage difference will become zero. So till when the voltage difference will exist, the voltage difference will only exist till the time the magnetic field is varying. If there is constant magnetic field, there would be no voltage difference which would be developing across this particular coil. Now what about magnitude of the voltage difference? Magnitude of the voltage difference is proportional to the rate of change in the magnetic field. So these are the two things that we need to take care of while we study electromagnetic induction. So as we discuss this electromagnetic induction, application of electromagnetic induction can be applied on, or can be studied through, the concept of electric generator. So I'm getting into electric generator. So let me check in your book what kind of generator it has been given. So AC generator has been given in your book. Okay. Apart from it, what has been given? Okay, Lenz law has also been given. Guys, give me a moment. Hello. Yeah. Okay. Sir, good afternoon. Tell me. Okay. Yes. Sir, what happens is my class and Raghavendra class both has been scheduled in same classroom 316, but because the next classroom is empty, so sometimes I go to the next classroom, or no, not opposite, just just behind 316, whichever classroom is there. So okay. No, it's not next to Mr. Pawan's office. It's next to the washroom. Yes, so just near to Miss Sonia's office, room number 316 is there. And no, I don't go to the opposite room also. J no, not near the staircase. On one side we have this. toilet. On the other side there is a classroom. So across the aisle on 317 or 318, one of them. Right in front of the lockers. That's the same. No, I don't go. Raghavendra is going now to that class. Yes, yes. Okay, sir. Right. Thank you. Bye. Okay, got an urgent call. So let me take you through the Lenz's law. What is Lenz's law? So try to understand what Lenz's law says, that direction of the induced current is such that it opposes. So it's actually Newton's third law, or law of inertia, whatever you can say. Lenz's law is application of law of inertia, or every action has equal and opposite reaction. So by Lenz's law, what it tells, that suppose this is my conductor, and there is a varying magnetic field which is coming like this, and it is crossing my conductor, and due to this a voltage difference is produced across it, and due to this voltage difference a current is produced in this. I have already discussed it. Now what would be the direction of the current? So Lenz's law defines the direction of the current produced in a current carrying conductor, because of when it is put inside a changing magnetic field. So Lenz's law tells me that the direction of the induced current, this current which is getting induced uh, due to this varying magnetic field VMF, would be in such direction so that it can oppose the change which produces it. It means that whichever magnetic field is producing this particular current inside this conductor, the current would be in such direction so that it can oppose this magnetic field. So what happens is that, or let me directly go to how to find out direction of current. So direction of the current by Lenz's law can be find out by Fleming's right hand rule. Fleming's right hand rule tells me that, suppose this is your thumb, this is your thumb, this is this is your index finger, and this is your middle finger. So middle finger, I'll make it like this. So middle finger shows the direction of the induced current, and your index finger or forefinger will tell you the direction of the magnetic field, and your thumb will tell you the direction of the force or the motion, because motion will be always in the direction of the force. So what happens is that in Fleming's right hand rule, we take three fingers. The three fingers used are, I am writing here, the index finger tells me the direction of magnetic field, middle finger tells me the direction of current, and thumb tells me the direction of induced, sorry, motion or force. So this is how it is. So Lenz's law is all about determining the direction of the current induced, and the principle to determine the direction of the current is that the current would be generated in such direction so that it can oppose the incoming or the crossing varying magnetic field. So the current would be developed in that direction so that it can oppose the magnetic field which is due to which this current is created. And for that I have Fleming's right hand rule. So I have given you three fingers, you can apply that, and you can write it down in exam. Now let me go to alternating current generators or dynamos. So alternating current generators are also called dynamos. Now, in your book, a figure has been made. Let me check the page number for you. On page number 29, all of you just go to page number 29. No, Ruhi, motion does not refer to the motion of magnetic field. It's not, see, the motion which has been kept over there, or the moment which has been kept over there, is not the motion of the magnetic field. It's the force which is getting applied. So actually, when a current carrying conductor, you know that a current has started flowing on in the conductor, and it is placed in external magnetic field, there would be a force developed in that magnetic field. So that's the direction of the force, as simple as that. Okay, so all of you go to page number 29 of your book. So a construction has been given. I'm just reading the construction and I'll explain you from your book itself. So what is the construction given? So as I start, AC generators. AC generators are also called dynamos. Now, what is the main function of generators? So electric generators convert mechanical energy into electrical energy. And alternating, why it is called alternating current generators? Because if electrical energy is getting generated, so what kind of current is getting generated into it? So it is called AC current generator, because the output of the generator is AC current. So you should not feel that input is AC. It has been named AC generator because the output, the current which is coming out of the generator, is AC. That is why it is known as AC generator. Now let me go to the principle of it. The principle said that it works on the principle of electromagnetic induction, where the magnetic flux through coil changes and induced current is produced. So how does it happen? It has been explained in the construction. So in electric current generators, what happens is you have magnetic pole, and inside the magnetic pole is fixed, and inside the magnetic pole, I mean in the space between the magnetic pole, the coil is kept. Suppose the coil is named ABCD. So what happens is I rotate the coil. If I rotate the coil, what will happen? If I rotate the coil, the magnetic field passing through the coils will keep on changing. How it will keep on changing? So magnitude remains the same, but what about the direction of the magnetic field? Tell me. Suppose I have a coil here. Suppose I have a coil here, and this I'm rotating like this. So it is kept between North Pole and South Pole, and this is getting rotated. So how it is getting rotated? So try to understand this coil is coupled with a driver here which rotates it. So this driver is rotated, and as soon as this is rotated, this coil is also rotated, and once the coil is rotated, there is a changing magnetic field through it, and due to this change in magnetic field, a current is generated in the coil which is received outside as the output current. So this is what electric generator is. So electric generator is a concept of electromagnetic induction. So now I'm going to your book. So your book tells that alternating current generator consists of rectangular coil ABCD called armature. So what is armature? Armature is the coil, rectangular coil which we are using. The armature coil consists of large number of turns of insulated copper wire wound over the soft iron core. The coil is kept between poles of strong magnets R1 and R2. R2 slip rings connected to two ends of the coil and convey the current produced outside the circuit. So see, what I'm trying to explain is the same thing I have told you 5 minutes, 2 minutes before. That what happens, the coil keeps on rotating, and as soon as the coil will keep start rotating due to induced voltage difference, induced current would be generated, which would be received outside, and that would be output of the AC generator. Now how does it work? So working principle also I have explained it to you, that one second. Working principle also I have explained it to you. So go to the other page, the working principle has been given to you. So what happens on the other page, on page number 30, it has been shown that between north pole and south pole, two coils have been kept. Sorry, a coil has been kept, and coil is getting rotated, and through brushes the current are coming outside. So that is what the principle is. Now what do you mean by AC current? So AC current means, I'll discuss that in class in details. Now you understand that what difference between DC current and AC current is that DC current will never change its direction. AC current will change in direction. So that is why in your book it has been written that AC current changes its direction 100 times in 1 second. So the frequency becomes 1 by 100 in India. So that's how it is. And now application has been given. One thing which is very important and is asked in the examination is difference or advantages of AC current over DC current. So uh, one thing which is how it is economical, I'll explain you in details. The second thing is the most important benefit of AC current or AC voltage is it can be step down or step up easily. So I have already explained to you that the transmission of the power happens at very high voltage. Why it happens at very high voltage? Because we need to lower down the current. Why we need to lower down the current? We need to lower down the current because I square R losses are there. So having when a current carrying conductor having current I is flown through it, the power loss would be equivalent to I square R. So more the current passing through a current carrying conductor, more the power loss. Hence, we need to reduce the amount of current through the transmission line. To reduce the amount of current through transmission line, we use transformers. In some time, I'll teach you transformers also. That is also based on the principle of electromagnetic induction only. So to reduce this I, what I do is that, so what happens in transformer, try to understand. Transformer, this side I give some input. As I give input, there is alternating current into it. Due to alternating current, what happens on other side, I have another coil. As alternating current is flowing through this, alternating current will produce varying magnetic field. Due to varying magnetic field, as this varying magnetic field will cross sectional area of this coil, as varying magnetic field is there, a current would be established on this side. This is the principle of transformer. So what happens is that, how many of you are there? Can you please give your attendance now, because people are leaving? Then why do they tell me to conduct classes when they are not interested in it? People who are there, give your attendance quickly. Ruhi is there. Who else is there? Kirtana is there. Who else is there? Only two people I am teaching now. Okay, no issues. Just look at here, guys. I'll explain you transformer first, and then I'll go to advantages and disadvantages. So look at here. So transformer, what happens? Have you guys studied transformers? Is it there in your syllabus? Let me just check. Yes, it's there in your syllabus. So let me teach you transformers, and then I'll come to. So what happens in transformer is that here input coil is there, or primary coil is there. Input coil is also known as primary coil. Why do I call it input coil? Because input current, suppose a current is coming from generator, and I need to step down the current, or I need to step up the voltage. So the current which is coming, suppose this is generator, and from here, from the brushes of generator, I am feeding this current to the coils of the transformer. And what happens, this goes, and this is AC current. So on the other side of this, we will be having secondary coils. Now why this is called secondary coils? Because try to understand, this is core type transformer I have taken. Shell type transformer has been given in your book. There is no difference in the construction of the shell type is different. The principle remains the same. So try to understand what happens is, whenever this current will go, always remember this AC current. So I have told you that magnetic field produced due to a current carrying conductor is this. If this I is changing, which is changing in AC current, so this magnitude or the direction of the, because I is changing in its direction. In AC current, what is happens, AC current is denoted like this. I is equal to I naught sine omega t plus phi. So it means that this is a sine curve. And what, how the sine curve is? Sine curve is something like this. So if the current is sine curve, it means that for some time it is positive, and for some time it is negative. What do I mean by positive and negative? I mean by positive and negative, what I mean by positive and negative is that sometimes it will be flowing in this direction, and half of the time it will be flowing in opposite direction. As the direction of the current is changing, what happens over here is the direction of the magnetic field produced due to current in the primary coil will also be changing. I mean, you will have varying magnetic field over here. There would be change in the direction of the magnetic field. As the direction of the magnetic field would be changing, due to that a voltage would be developed across the two terminals of the coil. Due to this induced voltage, a current would be generated in this coil, in the secondary coil, and which would be collected by the other wires, which is called the grid system. So it will go to the grid. Is it okay? So what happens over here is, the fundamental of transformer is that there is one thing called transformer ratio. What do I mean by transformer ratio? Transformer ratio is, or you can say that the power transferred from this side would be equal to power transferred on the other side. And what is the power? Power is known as V into I. So power may be, on this side, input current I write VIII, and output voltage I write VOIO. So what happens here is VO, or let me write it like this: VI by VO is equal to IO by II. So you try to understand, if VI is more, it means that if input voltage is more, then output current would be more. Because if here numerator is more, here also numerator would be more. If output voltage is more, to keep this multiplication equal on both the side, VO will reduce. So if try to understand, if voltage is VI here and VO here, if VI is input voltage is greater than output voltage, it is called step down transformer. What do I mean by step down transformer? Step down transformer means the, no, Kirtan, I saw your message, doubt now. The coils are of same material both the sides, but the number of turns are not same in both the sides. So what happens is, there is another relationship which says that if N1 turns are here and I am sending a current I1 to primary coils, and in secondary coil N2 coils are there, N2 turns are there, so N1 I1 will be equal to N2 I2. So what happens is, I2 by I1 is equal to, sorry, this I've written it wrong. This would be I1 by N1 is equal to I2 by N2. So N2 by N1 is equal to I2 by I1. So what happens, whichever side more turns would be there in the coil, that side more current would be generated. So in a step down transformer means I am reducing the voltage. Reducing the voltage means, to keep the power same, I am increasing the current. So what happens, I increase the current. Increasing current means, you should know that if you have to increase the current, you have to keep more number of turns here. So whichever side more number of turns are there, that side more number of more magnitude of the current would be established. Now in that particular scenario, or in case of transformer, look at here. So what I told you initially is that, generally here, when the current comes from the generator, I need to reduce the current on the other side, on the secondary side. So if I have to reduce the current, it means that if N2 coil turns are here and N1 turns are here, and current has to be lesser than this primary coil, it means that N1 has to be greater than N2. If N1 is greater than N2, then I1 will be greater than I2. If I1 is greater than I2, as VI has anti-proportional relationship, V2 will be greater than V1. It means that output voltage will be greater than input voltage. As output voltage is greater than input voltage, this is called step up transformer. So this is the principle of transformer. Now, how does it happen? Now, so I was on AC generator and AC dynamo or AC generator, and I was telling you that why a AC generator is better than DC generator. So, a AC generator is better than DC generator because first thing I told you that their stepping up or stepping down the voltage is easier in AC generator. The second thing is the electric current can be transmitted to distant places without any significant line loss. What happens in DC current, as the current is never changing, the losses are more in DC current, the losses are very less in AC current. So benefit of having AC generator over DC generator is it is economical, stepping up and stepping down the voltage is easier, and line losses. What do you mean by line losses? So wherever power is generated, that point is called power station. From power station, that power is transmitted to different distribution houses. Now in the transmission of the power, I square R losses are involved. For AC current, those I square R losses are lesser as compared to the DC current. So these are the three main advantages of AC generator over DC generator. Disadvantages. So disadvantage is one, as it is always changing, there is some peak voltage because it is sine value. So you can understand that V is equal to V naught sine omega t I am writing. As the value of omega t will keep on changing, value of V will keep on changing. So as soon as this becomes omega t becomes 90 degree, V becomes its highest value V naught. And suppose you touch or get a shock when V is equal to V naught, it's very dangerous for you. So peak voltage is dangerous in this case, and there are different uses, like they have given electro typing and electro refining and all those things. So in that, AC current cannot be used, in that only DC current can be used. So those things are very important. Okay, so any other doubt that you guys have, you can send me. Okay, any other doubt that you guys have? Okay, conversion of moving coil galvanometer to okay, so I'm getting two, three doubts. One second. Just let me go through it. Okay, let me just open that conversion page, then I'll tell you. So, Ruhi, try to understand. You have asked a question that why AC losses are lesser than DC losses. So, AC losses or DC losses will all depend on the current. Now, what happens in case of AC current? I can step it down. So, I can bring it down to a level where it is optimum, where I can afford that loss. DC current, I cannot. Whatever DC current I am producing, the same has to be transmitted. So suppose I am producing suppose 100 ampere AC current and 100 ampere DC current, and both has to be transmitted. 100 ampere DC current will have to be transmitted in form of 100 ampere. 100 ampere AC current can be converted, I mean can be stepped down with the help of step up transformer, where I increase the voltage and take the current down, make it from 100 ampere to 10 ampere, and with the help of that 10 ampere current I transmit it. So what happens is that as the transformers can be used in case of AC current, why it is possible to bring down the current level in case of AC current. As I bring down the current level in case of AC current, it is possible for me to reduce I square R losses by reducing the value of I. So I'm not saying that you can directly compare AC current and DC current losses. When the value of the current is same, the loss would be same. But as the value of the current can be reduced with the help of external equipment which is known as transformer, hence by reducing the current, the losses can be manipulated. That's what the answer would be for your question. So now let me move to okay. So let me move to changing of one second. So go to the page number, which page number it is, all of you. I'm just referring your book. I will uh, teach you from your book itself. Okay. So what is an ammeter? Ammeter, as I have already told you, that it is a device to measure current in any circuit. So what happens is how do you convert a galvanometer into an ammeter? So construction has been shown in a particular in the particular diagram on page number 23 of your book. What happens is the construction is like this. So you have a galvanometer. You have a galvanometer. So we have a galvanometer for our reference. So here is our galvanometer, and a current is passing through it. Current I is passing through it. Now what I do is that I put a resistance in parallel with it, and this particular diagram, I'll explain how it is used. So this is used as an ammeter. So what will happen is, obviously there would be some resistance over here. So the current would get divided into two parts of this circuit. So suppose the current going over here is Ig, and current in this particular part would be I minus Ig. Now see what happens. Okay, so now listen to me how it happens. So an ammeter is connected in series with the element so that the current is to be measured actually passes through it. So what happens, you always see whenever I make a circuit, what I do is that I put an ammeter in series with the circuit. Why I put ammeter in series with the circuit? Because I have told you that series connection of any particular equipment means same current will pass through that particular thing. So that is why it has been written in your book is that the ammeter is connected in series with the element so that the current, because whatever current I want to measure, I want to measure it directly. So it passes through that. In order to ensure that its insertion in the circuit does not change the current, an ammeter should have zero resistance. So ammeter is designed to have been very small effective resistance. In fact, an ideal ammeter should have zero resistance. An ordinary galvanometer is sensitive instrument. It gives full scale deflection with a small current of few microamperes. To measure large current with it, small resistance is connected in parallel with the galvanometer coil. Why do we connect parallel? See, here I have used this galvanometer. What will galvanometer do? Galvanometer will detect the current. Then why am I using this parallel resistance with this? So try to understand. Let me make two parallel resistances like this. So what happens? Suppose this is 2 ohm and this is 2 ohm. So 2 ohm and 2 ohm, if I find out the resistance of it, 1 by R will be equal to 1 by 2 plus 1 by 2. How much it is? It becomes 2 by 2, and 2 by 2 is equal to 1 by R is equal to 1 ohm. So R is equal to how much? 1 ohm. As simple as that. So this is how it is. So this parallel current, because the resistance over here has to be very small. If I take resistance of galvanometer, suppose this is Rg. I want this has been put in series. I want this particular resistance to be very small. Suppose suppose this resistance is not small. How can I make this resistance very, very small? So put a parallel resistance to it. The combined resistance would be very, very small, and you can find out the value of resistance passing. You can find out the value of current passing through it, and and the current can be measured. So that's what it has been written. So conversion of galvanometer means you have to put it in the series with the in series with the current carrying conductor or in the circuit. Why it has to be put in series? Because in series the same current would be passing through it. The second point that we need to take care of is that the resistance of the ideal ammeter should be zero. Generally it is not zero. So to make it zero, what do? We shunt it. So that is why it has been written in your book that resistance connected in this way is called a shunt. Only a small part of total current passes through galvanometer and remaining current passes through shunt. So in this way the current measuring happens over here. So did you understand this concept? Yes or no? Tell me. Okay, great, fine. So that is how that you can understand. One second, let me go to voltmeter now. Now voltmeter, what will happen? Voltmeter would be connected in parallel because I want voltage to be same. So voltmeter has to be connected in parallel, but the current passing through that should be very, very, very less. So what will I do? I'll put a resistance in series. That is why resistance in series. Why do two things again? Two three things in common which I want here is how do I measure voltage? By putting things in parallel. So I put things in parallel. How? So I will put galvanometer in parallel to the points where I need to measure the voltage. But galvanometer will have certain resistance. I don't want small resistance here. I will like to increase the resistance so that very small current is wasted due to connection of this galvanometer. That is why with the resistance of this galvanometer, I will put a resistance in series. If resistance of galvanometer, suppose this is Rg, and the series resistance which I am putting with it, suppose this is Rs. So what will happen in that particular case? Rg and Rs, they will combine together and increase the resistance of this part of the circuit. As the resistance will increase, very, very less current would be passing through this galvanometer, and that's how the voltage would be measured across it. Now tell me, any doubt? Any doubt that you have? Okay, fine. So you guys are not saying. So now what I'll do, I have covered most of the portion of your book. What I'll do is that I'll wait for your doubts. If you have any doubt, you can tell me. I can um, take over those questions. Otherwise, I'll wrap up the class. Am I getting any doubt? Okay, Rui, you are saying that with increase in R, V across the galvanometer will also change. No, why will V across the galvanometer change? I am saying that current is passing through it. When the current is passing through it, it will deflect. Resistance has been put here. Resistance, why resistance has been put here? So that very small amount of one thing for perhaps I forgot to tell you that galvanometer is very sensitive to even a small amount of current. So why a galvanometer is used in place of ammeter? Because galvanometer can measure currents even in millimeters and something lesser than that. That is why a very small amount of current is going through it, and a very small amount of current will able to deflect the needle of the galvanometer, and the current would be detected, or the voltage would be detected. So reason behind putting this resistance is to increase the resistance in this path such that the circuit current is not affected that much. If there is change in circuit current, suppose the change is I, or suppose 5 ampere current goes, suppose I have, let me remove it for you. So suppose here I have put my galvanometer and I have put this resistance, and I have to measure voltage between these 2 points A and B. Now suppose 5 ampere current is going here, and if resistance is very small here, what will happen? Suppose 2 ampere current goes here. So in the circuit only 3 ampere current would be left out. So here the voltage VAB should be equal to, or VBA should be equal to, VAB should be equal to 5 ampere into resistance over here, resistance between AB. So 5 RAB. Now suppose 2 ampere goes here, it remains 3 RAB. Then when there would be change in, or there would be uh, error in the measurement of voltage, to remove this 2 ampere or to reduce it to negligible level, I will increase this resistance such that a small current goes over there, so that this VAB would be, this current which is 5 would be nearly equal to 5 into RAB. So that's how this arrangement would be made. Are you understanding it? Okay, fine. Any other doubt that you guys have? Ask me. Do you guys need any other class on Sunday or perhaps any other day? You can post it in the group. Okay, nobody is asking me any doubt, so perhaps I need to wrap it up. Any other doubt in this chapter or any other chapter, please ask. Okay, fine. Okay, so I'm wrapping up the session now. Thank you so much for attending the class. If you have doubt, you can still ask me, but I'm not getting any doubt, so I have covered up the portion I needed to cover. Chalo, thank you so much.